Enterprise networks generate terabytes of traffic daily. We capture it and assume we understand the system. But raw volume is just noise. The first barrier to actual comprehension is physical transport. Packets drop, connections stall, and routers reject traffic outright. The second barrier is structural. Even when packets arrive intact, they often carry proprietary, undocumented payloads that standard tools simply cannot read. When an analyzer encounters a protocol it wasn't explicitly programmed to understand, it stops translating and hands you a block of raw binary. We are going to build a complete diagnostic pipeline. We will start by verifying the health of the physical transport layer and then write the actual code required to decrypt proprietary payloads. True visibility requires both macroscopic flow analysis and microscopic protocol parsing. Before we inspect individual packets, we have to verify the overall health of the network flow. This chart shows a Wireshark I/O graph plotting network traffic over time. This lets us distinguish a temporary traffic burst from genuine, sustained system saturation. Plotting basic metrics like packet or byte counts only tells us volume. To locate a bottleneck, we need to measure the system's load. Load measures queue depth. Expressed in Erlangs, it calculates the number of concurrent requests waiting to be processed within a specific time interval. When that queue depth stays consistently high, the endpoint is saturated. The server simply cannot process incoming requests as fast as they arrive. Macroscopic load data isolates the variable. It proves whether an application is failing due to physical volume limits rather than a logical software error. Once we rule out volume, we drop down to individual connections and examine the TCP handshake. Measuring the exact physical time delta between an outbound SYN packet and the returning SYN-ACK packet isolates network latency. If that SYN-ACK response time is exceptionally high, say over 1/10 of a second, the physical routing infrastructure is the bottleneck. Sometimes the target responds immediately, but it returns a reset or RST-ACK flag. An immediate RST-ACK proves the physical line is perfectly clear. The target received the request, but the specific port is closed or misconfigured. Then there are TCP retransmissions. The sender transmits data, but the required acknowledgement never returns. The sender tries again, incrementally increasing the delay between attempts. This pattern points directly to an active line interruption or a completely exhausted end host. By analyzing TCP state flags and timing deltas, we mathematically eliminate routing and hardware variables before we even look at the application payload. We know the transport layer is functioning, but communication still fails because the payload itself is wrapped in an undocumented Layer 2 protocol. Standard Wireshark parsing successfully maps the MAC layer and the LLC header, but it stops at the data field, leaving a block of raw binary. The last legible piece of metadata is the LLC protocol ID, or LLC.PID. That specific hex value identifies a proprietary system. In industrial environments, this is often something like the Rugged COM Discovery Protocol, or RCDP. The core limitation of any native analyzer is explicit instruction. It cannot read undocumented structures on its own. To map that raw binary into a legible protocol tree, we have to write a custom protocol dissector. When native decoding fails, the analyst must transition into a developer, engineering custom logic to parse the payload. Building a native Wireshark dissector from the ground up requires writing a C plugin. The first structural requirement is defining a C array of header fields. This establishes the exact variables we expect to find in the protocol. We also declare a subtree array, usually prefixed with et, to visually nest and organize this dissected data within the application's user interface. To pull data from the packet, we use the core extraction function, prototree add item. This function requires strict parameters. We have to give it the specific byte offset where the data starts and the exact length of the chunk to extract. We also have to specify the endianness, like ENC big endian, to ensure the byte order is read correctly from the network, rather than reversed by local hardware. But raw extracted integers are often meaningless to a human analyst without further context. To fix this, we introduce the value strings macro, or vals, which acts as a programmatic translation dictionary. The vals macro dynamically maps a raw hex integer to a human-readable state, translating a 1 or a 2 into initialization or terminate. Writing a C dissector forces the Wireshark engine to adopt your custom syntax as a native structural truth. If we are dealing with an existing layered protocol and only need to parse the final payload, we can use a Lua post-dissector. Instead of recompiling the core application, a Lua post-dissector is injected dynamically. It runs only after all native Wireshark dissectors have finished their jobs. We bind the logic by explicitly instructing the Lua script to trigger only when it spots our specific llc.pid target. We extract the payload using extractedfield.range, isolating the exact raw buffer that contains the proprietary data. The Lua script then executes its parsing logic and appends the new, legible hierarchy to the very bottom of the existing dissection tree. Lua post-dissectors allow engineers to surgically augment Wireshark's capabilities on the fly, extending visibility without altering the core codebase. Total network visibility requires this complete two-phase diagnostic pipeline. Analyzing macroscopic TCP behaviors and timing deltas mathematically eliminates the physical hardware and routing infrastructure from the equation. Writing custom dissectors in C or Lua eliminates software opacity, cracking open payloads that native tools leave entirely unreadable. It is the process of taking chaotic, opaque data and forcing it through custom logic gates until it becomes perfectly structured, intelligible information. Network traffic is never a black box. It is a strictly structured dataset that can always be reverse engineered, provided you build the correct programmatic hooks.